In the PDP-11 videos, we outlined the architecture of the 11, which was introduced in 1969, although production models weren't available until 1970. It was based on some earlier work done at Digital Equipment Corporation that they canceled, but then they revived again. So the exact origins of the PDP-11 go a little bit back into the 60s. Also introduced in the 60s, in 1964 to be precise, was the IBM mainframe that we know today, the IBM System 360. And what you're seeing on the screen is 3 panels of the notorious IBM green card. It's faded over the years. It had a distinctive green color, but it's kind of faded. There are other panels to it, but these are the 3 panels that contain the instruction set. Now, the 360 itself is long gone, but the current IBM mainframe is derived from it. And all of the instructions and all the patterns you see on this page are still valid. They've just extended it. Much of the code is actually still written in this level of the dialect. They call them architectural levels and so forth. And what you see down the side, I know it's probably impossible to read. We'll jump in. These are the basic instruction sets. Some of them were optional. Some of the instructions were optional. The decimal instruction set on the early models was optional. Decimal, for example, add decimal. That was optional earlier on, but then it became standard. The floating point was actually also optional. It was sold as both a business and a scientific machine. As a business machine, floating point wasn't really all that needed, but this was the basic floating point instruction set. Now, in order to understand the machine, the thing we need to do is look at the instruction formats. That's the way I always believe. If you're going to understand a machine, you have to figure out how it's going to do its instructions. And these are the instruction formats. I'll try to blow it up here. The basic instruction formats that were on the initial machine. The IBM mainframe was an 8-bit byte-oriented machine. The word size was 4 bytes. Previous machines, and most of the machines at that time, were 6-bit character machines, and their word sizes were things like 36 bits, 18 bits, 12 bits, that sort of thing, where they contained an integral number of 6-bit characters. IBM was one of the first to go to an 8-bit byte. There actually was the Honeywell Raytheon Datamatic, which was an 8-bit byte that preceded it, but that machine didn't go anywhere. The machine is, as I said, an 8-bit byte. The coding system for alphabetic characters was IBCDIC, Extended Binary Coded Decimal Interchange Code. The rest of the world was using ASCII 6 for 6-bit characters. IBCDIC Extended was not related to ASCII at all, but it did have a much wider character set. Had upper and lower characters, case characters. It had many extra special symbols and so forth. The IBCDIC character set is actually on the back of the screen card. IBCDIC evolved over the years and it changed a bit, but it's still the principal character set on an IBM mainframe. There are others, of course, Unicode and whatnot. When the PDP-11 came along and other architectures, they went to ASCII 7. And most machines nowadays are, the PCs and that sort of ASCII 7 or Unicode or something like that. All right, it's a big endian machine, unlike the PDP-11, which is little endian. What that means, again, is if you've got, say, a 4-byte binary integer in memory, the byte you address on a big endian machine is the high-order byte. It's the byte that contains the high-order bits of the number. In a little endian machine, the byte you address is the low-order byte. It doesn't make any difference in the instruction codes because they're laid out just as you see. But it does. But in terms of if you were mapping data from an IBM machine to a PDP-11, you would have to reverse the order of things like integers and so forth. Now, in the PDP-11, it tended to write everything from right to left, whereas here it's all written left to right. So in other words, bit 0 is on the left and bit 15 is on the right. It's just the way they do it. In an instruction, and this is the RR instruction format, the byte addressed is the byte with the opcode in it. So this would be the byte addressed by, if you were addressing the instruction. And this would be the next byte. It's 2 half bytes here, but that would be the next byte. So this might be at location 1000. This would be at location 1001. This is a 4-byte instruction. The instruction length on the original architecture was 2 bytes, 4 bytes, and 6 bytes. That did change with time and when they added additional instructions. Initially, the opcode was just a single byte, which allowed for up to 256 opcodes theoretically. In the current architecture, the opcode can have a second byte. The opcode can be extended to a larger number. There's far more instructions now than there were originally, but the basic instructions are still the ones most people program with. So this is what the instruction formats look like. I should point out the addressing mode. When this machine originally came out, it was a 24-bit address, which kind of, in other words, 3 bytes was the address. And 24 bits, you can address up to 16 megabytes of memory, which sounds ridiculously small to us, but back in 1964, 16 megabytes worth of memory would be roughly the size of South Dakota. Memory was made from magnetic cores. It was sewn. It was just ridiculous to think of a memory that large. So picking the number 24 bits or 16 megabytes was, they probably had a good laugh, saying, well, no one will ever build a memory. Another problem with the memory is not only the physical size, these boards, this is before semiconductor memory, these boards of iron cores, hand sewn, were physically quite large and heavy. If you built a large memory, say a megabyte of memory, the timing from one end of the memory to the other end of the memory was different. So if you fetched a word from the nearest part of memory, nearest to the CPU, you got it in so many, milliseconds, I guess, in those days, microseconds. But whereas you fetched from the other end of memory, physically further away, it took a different amount of time, quite a bit different amount of time. So that was one of the restrictions on the largest memory you could have in the old core memory days, is the timing restraints, because if you had to allow time for the worst case scenario, and if the memory got over a certain size, it would take too long to fetch some data. You'd slow the whole machine down. You had to slow the clocks down and everything. So they made some compromises, and I know my first large IBM mainframe, which was an IBM Model 67, 360-67, it had 1 megabyte of memory. That was the maximum you could put on it. Anything larger than that, you get into timing problems. And that was a machine that filled a building. It was a very large machine. In those days, what they did is they had a 2 megabyte attachment, which behaved like an I/O device and was 13 times slower than regular main memory. And they used that instead of a disk drive to store page in and out frequently used modules. But so the 16 megabyte limit was considered very generous originally, but of course in the 70s, when we started getting semiconductor memory and it got larger and larger, it was obviously an issue. The current machine uses a 64-bit address, and therefore, at least for the time being, that seems to be a ridiculously large amount of memory. The current machines can have vast amounts of memory, and what they did was the same as other computer manufacturers. They just extended the sizes of the registers. That's what Intel did. That's what AMD did to come up with the 64-bit architecture, which then Intel glommed onto. It's basically what Digital did with the PDP-11 when they went from 16-bit registers to 32-bit registers. It's a fairly common thing to do. Anyway, it worked. So what we're looking at, let's go back to the 16 megabytes, 24-bit address. It doesn't have any. The 24-bit address was almost always stored in a full word, in a 32-bit 4-byte word. So the problem that developed with the 3-byte address is that it was always stored in a 4-byte word, is that programmers were tempted to use that high byte. And a lot of code was written where that high byte that was not part of the address was used to store things, little messages going back and forth. And so a lot of old legacy code has to be run in 16 megabyte or 24-bit compatibility mode, which the current machines will do. You just tell it you want to be 24 bits and everything's fine. Otherwise, it would see these odd high bytes and say, what are these? and you would assume they're part of the address, but they're not. Anyway, it's just an issue with old code. Now the basic idea here is, again, we have an 8-bit opcode. And you see in all of these it's an 8-bit opcode. And most of the coding is done in the 8-bit opcode. Now admittedly, in the newer architecture, the extended architecture, there can be 2 bytes for the opcode, or more than 1 byte, I should say. The machine had 16 registers. It still does. 16 general purpose registers. It has multiple register sets and things like that nowadays, but basically at any given point in time you can see 16 general purpose registers, cleverly numbered 0 through 15. They're for the most part all the same. The registers all do the same thing, unlike the PDP-11 where registers 6 and 7 were the stack pointer and the program counter, or registers 13, 14, and 15. I think it's like 12, 13, 14, 15. In the VAX had special meaning. In the IBM mainframe, the registers were, for the most part, all equal. There is, I say for the most part, because register 0 is a bit different. Register 0, if you use it in the calculation of an address, it means no register, no contribution from a register. Otherwise, it's perfectly usable for arithmetic and things like that. By convention in the machine, certain registers are used for certain things. This is a software convention. Registers 14 and 15 are linkage registers. Register 13 points to a save area. Registers 0 and 1 are used to pass parameters to a subroutine and to return values. But that's software convention. It doesn't. And when there's another thing we use here called base registers. These B's all around here. Base registers are often starting off with register 12 and descending. Don't have to, but that's the convention. All right. So what do we have here? Well, we've got an 8-bit opcode, and we've got 2 registers specified. And what normally happens in an RR instruction, see RR means register register. Both operands are in a register. Is that the second operand is done unto the first operand, the result remains in the first operand. That's the usual case. Now if I can drag this thing over here, we'll see an RR instruction up at the top. You see these are the assembly language words for them, and the add. We have numerous add instructions here, but the one that's AR, all the RR instructions, I think all of them, ends in an R. There's the opcode. It's 1A in hexadecimal. There's the format. It's an RR format, and it's got 2 operands. And what happens in an add instruction, an RR type add instruction, is the 32 bits in the register specified as the second operand are added to the 32 bits of the register specified as the first operand, and the result replaces the value in the first operand. You add the second operand to the first operand, and the result is in the second operand. There are other add instructions, as you can see, and we'll get to them. You can see the format down here. There's a bunch of RRs. Generally speaking, they're going to end in the letter R. All right, let's go back down here and look at the next one. The next one is the RX instruction. The X stands for index, and you see there's an X in it. First of all, we got an 8-bit opcode. We have a register 1, which is the first operand, and then we have the second operand. The first operand is in a register. The second operand is in memory. The second operand address in memory is calculated by adding what we call the base register, B2. You put a number in here, the number of a base register. The sum of the contents of the base register plus the contents of the index register plus the displacement. That'll give you an address in memory. The displacement is 12 bits. It's unsigned. It's from 0 to 4095. That is the displacement in the original 360. The normal mode that most people in most of the time programming, for example, you notice there was an RX add instruction right under the AR back on further up on the card, is that base and displacement are used to address a value in memory. The index register in most cases is 0. When it's 0, it means does not participate. That's that special case. The only special case for the registers is the well, and technically some other special cases, but the basic special case is that if you specify a register 0, it means no contribution. You specified any other register here, the value in it would contribute to the calculated address. I say some other things. There's some instructions that automatically set some registers, and those registers are predetermined, but that doesn't really change the nature of the register. It's just a behavior of instructions. All right, why is this so? Well, the base and displacement give you a point in memory. This was really to make Fortran programs run quicker. This was an index register. You'd increment the index. The base and displacement would give you the origin of an array, and you just increment the index register and chunk. You'd go through an array quickly. That's what it was there, and it's called an index because it was, and still is, used as an index into an array of data. This whole displacement thing, nowadays displacements can be larger in some cases, but the base instruction, the RX instructions, was still there and is still widely used. What was the purpose of this? First of all, it means program segments tend to be 4096 bytes in length. They can be larger, but you have to have more than one base register. So what was the purpose of this? The purpose of this was to create relocatable code that you could put anywhere in memory. A module that could go anywhere in memory. There were no or very few absolute addresses in the module. So everything was relative. Relative to what? Relative to a base register. So in a module, a relocatable module, the first thing it did was load the base register with where it is. And the base register usually points to the very beginning or a few bytes into the beginning of a program. And then all the addresses were calculated relative to the base register. And so it didn't matter where you put the module, as long as the base register got loaded, and there is an instruction to load them, with an absolute address. It was absolute address plus a displacement, take you anywhere within 4095 bytes of the pointed to by the base register. Well, what if your program was more than 4095? Well, then you had to play games. You still do. You have to have more than one base register, or you have to reload the current base register, or you set it up as a subroutine, which will use a different base register. So the base register becomes part of the dance that you do when you write code for a mainframe. Still is. Nowadays they have longer displacements, so the modules can be bigger for some instructions, not all. The basic RX instructions are unchanged. And there is some relative addressing relative to the current value in the program counter, similar to the PDP-11. But this was how relative addressing, relocatable addressing was achieved. Now in the PDP-11, a lot of this was done by program counter relative addressing. Program counter became the register then you had a displacement from that. So and that's how they avoided, in many cases, absolute addresses. All right, so the base plus displacement and possibly an index will give you the address of an operand in memory. Shall we see one? Yes, let's go back up here and look at the next add, which is just plain old A. That's the assembly language mnemonic. Opcode is 5A. You'll notice there's a certain similarity here in the opcodes for the add instructions. Add logical is a different sequence. These instructions here are for signed arithmetic. The add logical is for unsigned arithmetic. Okay, the add logical does not understand signed numbers, whereas these adds all do, and you can get overflow as a result. They have positive and negative numbers and all that sort of thing. Anyway, here's the RX. Now, if you were to write it out explicitly in assembly language, this is how you would do it. You would put down the register designated as the first operand, let's say register 5. You would write down a displacement. You'd put usually, let's say, 0 for the index register, and you'd write down the base register, which means technically that I would have had to compute the displacement relative to the base register of the second operand. You notice all the second operands have 2s on them, and all the first operands have 1s. In reality, you don't. In reality, you write it symbolically. and you would put a label as the second operand. And the assembler will calculate. You tell the assembler where the base register is pointing, or will point, and the assembler will calculate the displacement from the presumed base register location to the label. So it fills in the displacements for you. You don't have to do it. You can play with it a little bit, but normally you don't fill in the displacement. So that's an add RX instruction. Getting those two out of the way, the rest becomes somewhat similar, easier. The RS instruction there's several specialized instructions here. It has a first operand, which is a register, a third operand, which is a register, even though it appears second. It's the third operand. There's a reason why it appears second. And the second operand is a base and displacement, no index. What was the index register becomes R3, and it's used for certain specialized, like looping instructions and so forth, where you need two registers. They are independent of one another. But the base displacement calculates the address in main memory. The SI instruction has a base displacement as the first operand. First operand is usually the target. The first operand is the one that's modified. The second operand is called an immediate operand. Notice it's 1 byte. It's an actual piece of data. It's 1 byte of data. And that data is done unto whatever's addressed as the so-called first operand, even though it appears physically second. This is the second operand. This is the first operand. They're called SIs. For example, exclusive or immediate. The value in the immediate operand, which is part of the instruction, it's a constant, will be exclusive ORed with the byte addressed by the first operand. So you exclusive OR this with that, and the result stays there in the first operand. So as an example of an SI. Then finally we have the SS instructions. These are storage to storage. RS means register storage, SI means storage immediate, and SS means storage. There's two flavors. There's the flavor that has the second flavor first. Let's go there. The second byte of the instruction is the length of the data. It's presumed that both operands are the same length. Excuse me. The operands are specified in base displacement format. The first operand is a base displacement format. The second operand is a base displacement format. For example, if I'm comparing two strings, this would be the address of the first string. This would be the address of the second string. This is the length. This is how many bytes to compare. An example of the single length SS instruction, as I mentioned, is the compare. Let's see, CLC, compare logical character. It compares two character strings byte by byte and sets the condition code accordingly. The condition code is 2 bits that reflect whether or not one was greater than, less than, equal, overflow, the usual conditions. And the opcode for a compare logical is D5. It's an SS instruction. This is the format if you were to write it out explicitly in the assembly language. As I said, very infrequently do people write it out explicitly. You do it symbolically. But if you were doing it explicitly, this would be the way. The displacement 1 and base 1 and the length. Length appears here. And then the displacement and base for the second operand. And byte by byte, they are compared one with another until there's a difference. If there's a difference, then the condition code is set. If there's no difference and you reach the end, the condition code is also set. The number of bytes to compare is L, L being that single byte that contains the length. There's a small caveat on the length. Since a 0 length compare made no sense, a value of 0 means 1. Now the maximum value you could put into an 8-bit quantity is 255. 255 means 256. So when you look at the object code on an IBM mainframe and you look at a length, the length you're seeing is actually one length that will be executed. So if you see a 3, it really means 4. Now the other format has got 2 lengths. There's a length for the first operand and a length for the second operand. These are mainly the decimal instructions, where you have 2 numbers which are basically strings. They're in BCD format, and one can be bigger than the other. The first operand usually receives the result, and that says something about the length of the first one. It has to be big enough to receive the result. If it isn't, there's an error. So for example, let's go over to the adds again here, and we can see the add decimal. All right, the C means it sets the condition code, the D means it's a decimal instruction. P, AP, they're also referred to as the packed instructions because the format, the BCD format, is also called packed decimal. But anyway, it's FA is the opcode. It's an SS instruction, but it has two lengths. There's the displacement and the base. Again, if you were writing explicitly, the displacement and base for the first operand and the length of the first operand, and that's the displacement and the base for the second operand and the length for the second operand. And so the second operand, if it's an add instruction, the second operand could be like, say, 20, and the first operand could be 20,000. Obviously, 20,000 is going to be a longer string. Let's say their minimum length. I mean, this would be 1 byte. 20 would be 2 bytes in packed format or decimal format. And this would be longer if it was a large number, so you could have a difference in length. The only thing is, if you were adding two numbers, and you have to make sure the length is big enough to hold the result. Otherwise, you get an interrupt. But there's a bunch of these decimal instructions floating around, and they are all the instructions that use two lengths. Now, in the extended architecture, we go beyond this, and they started extending the architecture actually in the 1970s, where they went to even longer versions of the compare logical character. So, for example, if you're doing a compare logical character or a move character, the maximum you could move would be 256 bytes, and the maximum you could compare would be 256 bytes. Well, that's one of the first things they rectified, and they came up with a CLCL, compare logical character long, and an MVCL, a move character long, which didn't use an embedded. The length is actually embedded into the instruction. It's a constant. That creates other problems. But in other words, in the long instructions, they actually use pairs of registers, but they're not on the original architecture.